it's very low, and in fact, so that's a sign of that's a sign of delocalization, right? And so you've seen the inset participation ratio, which is basically just the inverse of the inverse participation ratio, and so participation ratio is very tiny in the normal phase, right? So only some of the states in this expansion are contributing, and you see that as the number of atoms is changed, so there is a spreading out, and so it's instructive to study how this PR varies as a function of the Hilbert space dimension. So that is actually the inset of the second figure. So you see that PR as a function of ND, I mean, it's increasing with ND, but it's going only as roughly like square root of ND, right? So that is a sign of multifractal nature. It's extended in nature, this ground state, but it's actually not ergodic. So these such states are called multifractal. And so this is also seen when you look at DQ. So you see that DQ is close to 0 in the normal phase. So it's localized there. Whereas when G is greater than 0.5 in the superradiant phase, you see that DQ is around 0.5 roughly. So that corresponds to this fit that goes as ND going as ND to the half, right? So this is one finding. And then so there's a couple of allied measures, so which I'll sort of quickly rush through because I want to get to the next point. So basically, you can study so-called Mayer-Woloch measure, which is like the purity of the state. And so again, these things and studied in the ground state itself show you that roughly the state is localized in the normal phase, whereas in the superradiant phase it's delocalized. So we also have some dynamic measures. So we did some quench dynamics. So we start in an eigenstate of the model at G equal to 0, and then you let it suddenly quench the Hamiltonian to some value of G, which is positive. And then you see that when G is greater than 0.5, you get a different kind of behavior as seen in the second figure. So second figure plots the saturating value of this concurrence, right? So concurrence is a measure of entanglement between two spins. And so you start seeing that there's a dramatic change beyond 0.5, which appears. And so this is also seen in this sort of phase diagram or a surface plot in figure C, where we look at actually quenching from different eigenstates. So not just the one particular eigenstate, but you can start with any one of the eigenstates at G equal to 0, and then you quench it to some other value of G, and you see that there is a significant difference in what happens to this quench if G is less than 0.5 and G is greater than 0.5. And interestingly, that is true no matter which of the eigenstates you choose. So it's really the quantum phase transition is what is being tracked by this quench dynamics. So this is one observation. And next we go to the so-called thermal phase transition. So there is a way to calculate this thermal phase transition. One can write down an expression for the partition function in terms of a double integral, right? So you can work with some kind of coherent state basis and so on, and do a few lines of algebra. And then so so this is in the superradiant phase. So you can actually work out this double integral using the method of steepest descent. And so you can argue that there is a temperature at which this method will break down, and that temperature is actually it signals the transition temperature. If your temperature is beyond this TC in the superradiant phase, you're going to get back the normal phase, right? So this is sort of there in the literature, but we sort of redid this calculation. It's there in the paper. You can look at this. But so there is an exact expression available for the transition temperature. Now, what is new from our perspective is this mutual information between any two spins. If you study mutual information between any two spins and see how this varies as you change G and T, right? So this is how mutual information is defined, and you're looking at a thermal state. So it's a density matrix, which is a mixed state. And if you study S1 plus S2 minus S12, it's a measure of like the total correlations, the quantum and classical correlations. So we see that when you're in the superradiant phase, actually, maybe let me start with figure C. So figure C is a surface plot of this mutual information between any two atoms with G varying on the x-axis and T varying on the y-axis. So you see that whenever G is less than 0.5, it doesn't matter how high your temperature is, you're always in the normal phase. So this mutual information um, is relatively low there. And then when G is greater than 0.5, and if temperature is sufficiently low, you're in the superradiant phase. But then as you increase this temperature, as is seen in figure A, so you see that the mutual information starts dropping. And in fact, this agrees very well with, so the dashed line is the curve from theory, from the analytical expression. So this shows, I mean, there is some kind of a scaling expression data in figure B. So basically, our study suggests that in fact, mutual information between any two spins is a good marker for this temperature phase transition. Just like what is already known is that if you just study the entanglement between the spins and the bosons, the quantum phase transition is well described by this, right? So the third kind of phase transition is the so-called excited state quantum phase transition. So here again, so we show data for the level statistics. So when G is less than 0.5, when you're in the normal phase, so you have this Poisson statistics, and when G is greater than GC, so you get Wigner-Dyson statistics. So this is the sort of conventional wisdom, but actually some finer studies suggest that it is a central band of the superradiant phase that seems to agree very well with the Wigner-Dyson. But if you look at bands which are above a certain critical energy and below a certain critical energy, in fact the statistics is somewhat mixed, but it's closer to Poissonian than Wigner-Dyson, right? So this is also confirmed when you look at the ratio of consecutive level spacing. So random matrix theory tells us that the value of this average of R should be around 0.53 if you're in for Wigner-Dyson, and it's for Poissonian it's going to be 0.39 or so. So the data here, see, I've looked at R average versus G. For the full band, if you're for G less than 0.5, all the energy levels behave pretty much in the same way. So you can study R average as it is, and it's roughly in the Poissonian limit. And then you see that if you make a distinction between the central band and the top band and the bottom band, you see there's a significant difference in R average. So the top band and bottom band, they are more like Poissonian, whereas it's only in the central band that you see that it's Wigner-Dyson. And so there is some literature, some studies in the literature which show eigen value properties, but we also study eigen vector properties and show that in fact this this feature is borne out there as well. So we study von Neumann entanglement entropy between spins and bosons, and also concurrence, right? So concurrence between spins, I have briefly indicated this, but this is somewhat a complicated object to explain, but roughly we can think of it as entanglement between any two atoms, right? So this is the data. So if you look at the eigenvector properties, I have these 4 different quantities I have plotted. So first one is von Neumann entanglement entropy between all the atoms and the bosonic field. So that the second one is similar plot, but for the mean photon number. So you see that clearly the von Neumann entanglement entropy is much larger in the central band, right, compared to the top and the bottom band. There's a clear distinction between the top, the central, and the bottom. And likewise, the bosonic, so the number of bosons is also significantly different in the central band. So, but neither of these two quantities cares about G greater than GC and G less than GC apparently. Whereas you see that if you look at concurrence between any two atoms, which is a property within the spin manifold itself in some sense, so that is able to also capture this G critical. So if you're in the normal phase, you get a different kind of behavior, and that is somewhat like the behavior in the bottom band. So figure C is about concurrence, and figure D is about participation ratio of the eigenstate, is also sensitive to this. So we see that the central band participation ratio, so that's blue is so higher value. So you get a higher value in the super radiant phase, and so the normal phase is somewhat like the bottom band and the top band, right? Although it's kind of a mixed behavior. Okay, so we have looked at the three kinds of phase transitions in the decay model. The quantum phase transition, with the aid of a study of the participation ratio and how it scales with the Hilbert space dimension, we argue that it becomes multifractal, the ground state, in the super radiant phase. The thermal phase transition, for which it's possible to obtain an exact analytical expression. So there is a phase transition if you're in the super radiant phase. And so we show that, in fact, this is very nicely captured by a study of mutual information between any two spins, right? And so there is an YIMQCMT in the super radiant phase. So that's the excited state quantum phase transition. There are two cutoff energies which are it's possible to discern, and the central band behaves significantly differently from the top band and the bottom band. So although there is some discussion about this in the literature, and so it's the lower cutoff is what apparently seems to be accepted as an YIMQCMT. The upper one is still a matter of debate. And so, but anyway, our findings suggest that this is very clearly seen even with eigenvector properties. It's not just eigenvalues. And in fact, we get entanglement entropy between spins and bosons, mean photon number, concurrence between spins, and participation ratio. All of them are able to show this the three bands and how distinct they are. Okay, thank you. Yeah, I think Aurab has a question.
Hi,
yes.
Can I? Yeah. So I had a simple question. So you showed these level statistics in one of your graphs, and you commented that it's sort of between Poissonian and Wigner-Dyson when you sort of So somewhere, right, in your parameter regime. So
right.
why is that happening? I mean, can you please elaborate on this?
So it's in the lower band and the upper band. So it's kind of a mixed behavior, I guess. It's so here, so you see that it's when G is sort of close to the phase transition, but not like deep into the super radiant phase. That's where we see values which are, I mean, where apparently the eigenstates are unable to make up their mind. So maybe if you go to very large system size, again, this may, I don't know if it's going to be like a clear transition or it's some kind of a crossover. That is not very clear.
Is there in some, okay, I don't know too much about this, but I mean, in some sense, does your Hamiltonian become long-ranged or something? Or, I mean, normally these two distributions are the standard distributions, right? So I was just wondering why you get such sort of signatures.
So these are standard distributions, but apparently here it's more complex in the sense that some part of your spectrum behaves in one way and another part of your spectrum is behaving in a different way. And moreover, so it's like, I mean, it cannot be it's not an abrupt thing. So there's like some part of it is still making up its mind and then it's slowly changing over. So that is one possibility, but I don't know. It's a finding. We are reporting it as a finding. So deeper understanding.
Yeah. Okay. Thanks.
Yeah. Srijit has a question and Manas has a question.
So you mentioned that the spin could be anything. So in your results, how does these things depend on the spin representation of sigma?
So you're talking about like the first slide, maybe, right?
Yeah. So how does these results depend on?
Well, I mean, we have studied it only for this symmetric case where we have just fixed J to be n by 2, right? I mean, other J's also should be explored, I would think. But I think this is where the numerics are relatively easy because the Hilbert space is now just n plus 1 times n max plus 1, right? So if you fix, like usually in spin models, we tend to fix the magnetization, right? If you do that, then the sizes involved will be exorbitant. But apparently, somehow this seems to be what people in quantum optics do. This is a standard thing. So I don't know. I mean, I think the other ways of looking at J should also be explored. I don't think they are sufficiently explored. Yeah, so we
Okay.
focused on this because this is apparently this is like the standard from what the literature survey we did suggests.
Okay.
Yeah.
Okay.
Manas also has a question. Oh, okay. Srijit, you want to have a follow-up question?
No, good, thanks.
Okay.
Yep.
Hi.
Yeah.
So there's a dissipative version of this model, right? Where it's also even the position of the critical point is sort of known when you have dissipation. So have you thought about this kind of analysis for the dissipative system?
No. So I think it would be interesting to do it. But is there a clear superradiant to normal phase transition there as well?
Yeah. So and even the I think in the thermodynamic limit, even the location of this critical point is known for the dissipative case. And yeah.
Okay, so my hunch would be that if there is a clear phase transition, then for sure these quantities should be explored there as well, because they are showing such clear signatures here.
Right.
And so we are thinking about some other generalizations of this model. So there is the Rabi model, which is the lesser version. Then there is also some anisotropic models where there are these well-defined phase transitions. So we are already doing some explorations there, and we are finding that many of these features will extend. So I would guess that it should go through for the dissipative model as well. So another possibility is to look at like open systems. That is also something we are thinking of, but yeah, I mean, surely, yeah, this is like a starting point, I would say, because I don't think there's any literature on these kinds of mutual information or density matrix kind of calculations are not there. But the ground states have been studied, and with entanglement properties and so on.
Right. Yeah. Okay. Thanks.
Okay, sure.
Are there any other questions?
Anumitra from Nexel. Hi, Aditya. Just a curiosity. I'm completely new to this field.
Okay.
I was just wondering. I mean, let's say I have a fermion system, so spinless fermions on a chain, and I bipartition the system in real space into two halves. Let's say.
Okay.
And based on that, on the occupation on the left and right, I restructure my Fock space.
Okay.
So does it make sense to look at bipartitioning in the Fock space and look for mutual informations on different parts to study transitions? I mean, where particle number fluctuations would be a part of the phase transition, assuming that.
So the thing is that if you want to study something like entanglement, you must have a proper tensor product structure, right? So then only it becomes lesser. So any overall state, if you can put it in such a way that it should be definable as some summation over coefficient of a basis state from one part of it and basis state from the other. If it's able to completely define every state, then yeah, of course, it's completely legit then. But does that happen in the way you're thinking?
Yeah, I mean, I think from the point of view of tensor product structure, one can certainly write that. I was just curious. I mean, we have done this in a different context, not in the context of information. I was just curious, bipartitioning in the Fock space and information between different particle number sectors in the Fock space, does it give something useful?
Well, it could. I don't know. So, but the thing is that first of all, you should be really sure that the tensor product state structure exists, and then of course, I mean, entanglement is an abstract thing. You can take your overall state and think of it in many different ways of thinking of subsystems. So any of such subsystems should be considered, because maybe one kind of breakup gives you more insights than another, and particularly this is useful if you think that a certain kind of subsystem is particularly relevant for some context. Like if there is one spin which is being treated in a different way, then that is the natural subsystem to consider. And likewise, if you believe that your Fock space there is some reason to partition that out, then it's worth considering. Otherwise, I don't know, it would be like a theoretical curiosity.
Okay, sure. I just wanted your comment. Thanks.
Yeah.
So are there any other questions? If not, then let's thank Aditya again for a very interesting talk.
Thank you. Thanks a lot for giving me this opportunity.
Sure.
Okay.
So maybe you can unshare your screen. So
yes, I'm doing that.
So we'll go on to the second talk, which is by Srijit from ICER Pune. Srijit, you can share your screen now. Great. So Srijit will tell us about energy transport and dynamics in chiral clock model. And I'll tell you after 18 minutes are over, Srijit. Srijit, can you hear me?
Yeah, I forgot to unmute myself. Sorry.
Okay. So I'll tell you after 18 minutes are over. Okay.
Yeah. Thank you. Thanks for inviting me to give this talk on our work on dynamics in chiral clock model. The presentation that I'm giving today is based on the first two papers, post-quench entropy growth in the chiral clock model and energy transport studies in the chiral clock model. Some of the results are based on some intuitions from a previous study on the same model. Okay, so this is the plan for the talk. I'll introduce the Z3 chiral clock model and present it in a way where I compare it with the 1D transverse field Ising model, which is probably more familiar to a larger audience. Then I'll talk about different domain wall types and the dynamics of sparse domain walls in the ordered phase of the model. Then I'll discuss the domain wall scattering at open boundaries and their effects on entanglement growth after quench near the boundaries and what that implies for the thermalization close to the boundaries. In the second part of the talk, I'll talk about MPS studies on transport properties of the chiral clock model. Okay, so the Z3 chiral clock model is described by the following Hamiltonian. It's there's a coupling constant which is complex valued with a phase theta, and a spin-spin coupling term, and a transverse field term. Again, the transverse field is complex valued, and all of these plus their Hermitian conjugates. The diagonal operator in the spin, which represents something like the magnetization sigma z, is the sigma operator, which is diagonal in a three-dimensional local Hilbert space. It has diagonal entries 1 omega and omega squared, where omega is the cube root of unity. And tau here is a cyclic permutation matrix. Sigma generalizes the Pauli sigma z matrix, in which the diagonal entries are square roots of unity, and tau generalizes the Pauli sigma x matrix, which is a cyclic permutation in two dimensions. And the whole Hamiltonian essentially generalizes the transverse field Ising model, which has a very similar form. The transverse field Ising model is Z2 symmetric, whereas this chiral clock model is Z3 symmetric. It has a Z3 valued parity operator, sort of generalizing the Z2 valued parity operator of the transverse field Ising model. The model has a broken symmetry phase for J over F larger than 1. And it's a threefold broken symmetry phase. For the parameter theta, which I mentioned here, it's the angle corresponding to the complex coupling constant J. If that is less than pi over 3, then I get 3 ordered phases, which can essentially be summarized at 1-1-1 phase, an omega phase, and an omega squared phase. And if theta is greater than pi over 3, then there is another set of antiferromagnet-like broken symmetry phase, where the ordered phases can be characterized by 1 omega omega squared 1, and omega squared 1 omega phases. As I increase the transverse field term, F, there is quantum fluctuations between these phases on these phases increase, and at some large value of J, at a small value of J over F, there is a transition to a paramagnetic phase. The precise phase diagram has been studied in this work. The So the transverse field Ising model is exactly solvable in the sense that, or due to the fact that after a Jordan-Wigner transformation, in terms of the transform variable, or the commutator of the transform variable with the Hamiltonian is linear in the transformed variables. And this allows us to construct the ladder operators. And this allows us, and that allows us to construct the eigenstates of the model. The chiral clock model can also be Jordan-Wigner transformed. The parafermionic transform variables, however, has a quadratic commutation relation with the Hamiltonian. As a result, it's not possible to construct the ladder operators, at least not in the same way. And therefore, this is not exactly solvable. The transverse field Ising model in the transformed variable has a boundary zero mod, which implies that every eigenstate is doubly degenerate. The Z3 clock model, however, doesn't have this property. Only the low energy modes are degenerate. We say that these have weak zero modes. Okay, so now we'll discuss the different domain wall flavors of this model. Since there are 3 possible ordered states, it turns out that there are 6 possible domain wall flavors, and 3 of them have 1 chirality, and there are opposite chirality versions of these domain walls. At finite value of theta, non-zero values of theta, it turns out that the energy of the opposite chirality domain walls are different. At finite value of phi, which is the complex angle, the phase corresponding to the transverse field, time reversal is broken. However, not much studies have been done on dynamics in the presence of non-zero phi. However, the phase diagram is known from DMRG studies. We will work with the case of phi equal to 0 and explore the effect of theta on various aspects of dynamics in this model. Okay, now that we know the domain wall flavors of the model, I'll present the effective picture of domain wall dynamics at weak densities. At weak domain wall density and small f, it turns out that the effective dynamics of the single domain wall can be written within perturbation theory as a free particle hopping on a lattice. The effective hopping parameter is then the transverse field term f, and the chemical potential of the domain wall particle is given by theta. The key point is that the domain wall energy depends on theta, and more importantly, energy of the domain wall is different for opposite chirality domain walls. So 1 omega domain wall has a different energy than the omega 1 domain wall. Okay, all these are in the case of phi equal to 0. If phi is not equal to 0, the system breaks time reversal symmetry. So we will restrict to this case. Now, given this effective model, we'll look at the properties of scattering of these domain walls at the boundary. Again, within leading order in the transverse field term, we can see what happens to these domain walls at the boundary. So it turns out that at the boundary, the f tau term takes a domain wall of 1 chirality and scatters it back into a domain wall of opposite chirality. So if I have a domain wall of the kind 1 omega, 1, 1, 1, omega, 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 traveling towards the boundary, it is scattered back as a domain wall of the type 1 omega squared. And this has to happen, if at all this scattering has to happen, it has to happen against the energy band gap because of the chemical potential difference for different domain wall flavors. This has to happen against the energy gap that depends on theta. Now, if this energy gap is large enough that the bands corresponding to different domain wall flavors do not overlap, then we will have that there is 0 probability for the domain walls to scatter into a opposite chirality domain wall. If the 2 bands corresponding to different domain walls do overlap, then there is a finite probability for the chirality to change at the boundary. So we can put in these conditions and find the condition on theta for the chirality change to happen at the boundary. And it turns out that at large theta, relative to the transverse field, there is no chirality change. And for small theta, relative to the transverse field, the chirality of the reflected wave is opposite to that of the incoming wave. So now we'll look at the results of entanglement growth near the boundary in subsystems near the boundary due to this. So before that, let me quickly remind you the effective picture of entanglement growth. After a weak quench from a fully ordered state, which is what we are studying by switching on transverse field, domain wall pairs of opposite chirality are nucleated from every point. These propagate away from each other, and in an effective picture, entanglement entropy across a cut, real space cut, can be seen to be proportional to the number of domain wall pairs separated by the cut. Okay, this is a cartoon showing this picture. The cartoon showing the linear combinations appearing in the final tiny walled state after the quench. At every point in the system, domain walls are created, and if a pair of domain wall crosses a boundary of a subsystem, then that contributes to the entanglement. Okay. At some large time, what happens is that the number of such separated domain wall pairs that are coming into the system matches that of the number of such pairs that are going out of the system. And at that time, the entanglement growth is expected to saturate. Okay. Until then, there is a linear growth in entanglement. Okay. However, and this is true in most systems. However, if you look at a weak quench, and if a system is starting from an ordered phase, and the quasi-particles are domain wall-like, then every time a domain wall crosses a system from one side to the other, there is a tiny fraction of the amplitude, a tiny amplitude for the system to be in a oppositely ordered phase. Okay. So every time a set of domain walls crosses the system becomes more and more likely to be in the opposite chirality, opposite ordered phase. So the result of this is that after a weak quench, the entropy keeps increasing even after the expected saturation. So this is the result of a TEBD calculation for subsystems near the boundary. You see that initially there is a linear growth in entanglement, and after the time where we expect it to saturate, you see a subsequent increase in entanglement. So initially what happens is that there are new domain walls that are entering the subsystem, and the subsystem is of this form. And after some time, the number of incoming domain walls match the outgoing domain walls. However, what happens is that as the domain walls go in, reflect at the boundary, and come out, the original ordered state, okay, this is the cartoon of a reduced density matrix of the subsystem. The original ordered state, which has a density matrix 1 and 0 everywhere else, after the domain wall exits the system, a part of the probability is transferred to the opposite ordered phase. So I've shown this region to be the part of the Hilbert space which has an ordering of 1, 1, 1, and this is the part of the Hilbert space where the ordering is that of omega, and this is the part that has an ordering omega square. So as the domain wall goes in, scatters to the boundary, and exits, some part of this is converted to an oppositely ordered phase, which is essentially the mechanism that leads to thermalization. Okay, so and that explains why the entanglement continues to increase even after the expected saturation. Okay, now coming to the chirality, effect of chirality. At small theta, the domain wall flavor changes at the boundary scattering. And a consequence of this is that, so this is a space-time diagram sort of the domain wall. If the initial region is ordered in a B direction, after a domain wall crosses it and gets reflected and comes out, oops, the arrow should be this way, B gets converted to C, or in other words, if initially it's 111 ordered, it gets converted to omega ordered. However, at large theta, as we discussed earlier, the domain wall flavor does not change upon boundary scattering, and therefore there is no change in the chirality after, no change in the ordering of the state after scattering of after the domain wall passes through the system. Okay, so this is the result for small theta, and these are the results for large theta. And we see that at large theta, the entanglement saturates instead of continuing to grow because of the effect that I just mentioned. Okay, what does it have to do with thermalization? It turns out that since continuously the system is getting converted to oppositely ordered faces as the domain walls are passing through the subsystem, ultimately the system will thermalize to zero magnetization after the quench. However, here at large theta, this doesn't happen, and therefore the binary fails to thermalize. And that's what is shown in this diagram. Vertical axis is the order parameter, and horizontal axis is the position. And various lines show different times, the magnetization at different times. In the small theta region, you see that the magnetization continuously decreases with time, leading to where we expect that ultimately it will go to zero. Whereas at large theta, about the cutoff that I discussed, the magnetization saturates to some value that is dependent on the distance from the edge, saying that the system is not thermalizing. Okay, now I'll quickly show the results for a slightly related but different calculation, again related to the transport properties, now related to the transport properties of the chiral clock model. Here we studied the effect of the chirality parameter theta on energy transport in the system. So we essentially used the Lindblad operator to mimic different temperatures at the boundary of the system, and studied systems of different sizes from 12 to 48 using matrix product states implementation of this Lindblad master equation. So most of the such studies have been done on spin or spin half models, and to my knowledge, this is one of the few studies which has gone beyond spin half models. And in spin half model, it has been known that integrable model typically imply that there is a ballistic transport. One goal here was to check whether this is valid even beyond spin half models. Secondly, we want to know what exactly theta does to the energy transport properties of this model. It is known from previous studies that there is a line of integrable points on the in the phase diagram. It is essentially j cosine 3 theta is equal to f that defines the line of integrable points. For when phi is not equal to 0, there is a so we'll restrict to the case where phi is equal to 0. So this term is 1. Okay. So this shows the level spacing ratio as a function of the chirality parameter theta. And as you see, at this point where we expected it to be integrable, we do get approximately Poissonian statistics. And away from it, we don't always get the GOE statistics, but something close to that, or at least something away from Poisson statistics. These level spacing calculations were done in very small systems of the order of 12. So there might be some finite size effect here. Okay, so the Lindblad operators were designed to thermalize the boundaries according to a Hamiltonian that closely matches the main Hamiltonian of the system. And the density matrix was implemented as a matrix product state by modifying the operator notation and definitions of expectation values. And we calculated the steady state current after the time evolution, after long time evolution.
Hi, Srijit, sorry to interrupt. So 20 minutes are over. So
okay,
yeah,
I'll just flash this result. Yeah, I'll flash the result then.
Okay.
So these show the current as a function of theta. Close to the integrable points, we get the maximal current that seems to be independent of the system size. This can be parameterized by the transport scaling exponent, which can be calculated from the current versus system size plots. And when we compute it, we get very close to ballistic behavior at the integrable point, but away from the integrable point, we get something that looks like super diffusive. We are not very confident because of finite size effect, but at the integrable point, we can confidently say that there's a clear ballistic transport, which is indicated by transport exponent gamma equal to 0. Okay, so I'll leave with the conclusion. And yeah, so we have basically studied the effect of the chirality parameter on various dynamical and transport properties in the system. Yeah, phi has not yet been studied. It's slightly harder to study due to bigger phase diagram. Yeah. Okay.
Okay. Thank you, Srijit. Are there any questions at this point? We'll check.
Srijit, I have just one simple general question. I mean, away from the integrable point, I guess normally the transport is expected to be diffusive. Is that correct?
Typically, yes. Not always. There are exceptional cases where this doesn't happen. But yeah, so it's typically expected to be diffusive.
I see. And these exceptional cases, why doesn't it happen? Is there like a single answer, or is it a very system-specific thing?
For instance, for spin transport, I think there are, especially in XXZ model, there is no simple connection between not integrability and
I see.
diffusive transport. Yeah, so here we cannot claim for sure. Sorry, not here. Here we cannot claim for sure that this is due to what the effect of not integrability is, but we can say for sure. What we can say for sure is that at the ballistic point, at the integrable point, it is ballistic. Transport is ballistic.
Yeah. And just one more quick question. I mean, since of course this result was based on this Lindblad analysis, so if you change your Lindblad operators a bit at the integrable point, I mean, does this ballistic scaling survive? I mean, I guess it should, but
okay, thank you for that question. We were also worried by that. So we did try, although I flashed only one kind of Lindblad operators, we tried two different kinds of Lindblad operator, one that inherits the value of theta from the main Hamiltonian, and one that takes theta equal to 0 irrespective of what the theta of the main chain is. Okay, so we used two different Lindblad operators, and qualitatively we got the same result. So the blue line is for one value of one set of Lindblad operators, and orange is for another set of Lindblad operators on the left, on the right hand side. So yeah.
Okay, so Victor has a question.
Oh, sorry. Yeah.
Hi. I cannot hear anything.
So Victor, can you hear us? Okay, maybe. So maybe Saurian, you can go ahead with your question.
Maybe it's a question and maybe it's a remark. Srijit, this model maps onto this parafermion chain, right? And we know that if you take fractional quantum Hall edge states, you can design within the Josephson junction, you can have these zero modes which are parafermi, Z3 parafermi, for example, with the 1/3 state. Now,
Yeah.
does it mean that there is a possibility of a Josephson array kind of setup which can mimic these chains? Has anybody tried that?
Yeah. So
Just curious.
okay,
I mean, this.
yeah,
No.
2 points. They may not fully answer your questions. The first point is that the parafermions are in a dual representation of the clock variables. So whatever result that I'm flashing here, they are when the local variables are the sigmas and not the parafermion. So many of these things don't transfer to the parafermion case. Of course, the phase diagram is the same. So the studies on phase diagram would be the same for.
But don't you
the
think even the
parafermion
heat transport will be the same?
No, they will be different because they are the one variable is not local in the other variable. The second point is that I think there is a set of papers by Jason Alicia and Fenley talking about some of these issues, but I'm not an expert at the.
Okay, but you are saying that the heat transport will be different. I mean, you expect.
Yeah, it will be. They all will be different
because of the coupling. I mean, what you couple, how you couple to it, right? The degrees of freedom.
Yeah,
that's the only difference.
Yeah.
If you treat it within statistical mechanics, you won't know the difference, right? Once you have the spectrum.
Yeah, I suspect so. Yeah, I think the local variables are completely different, so I don't think that the heat transport result will be the same.
Okay, thank you.
Are there any other questions? Okay, if not, let's thank Srijit again for a very interesting talk.
Thank you.
Okay. So now we move on to the last talk of this session. And this is by Shubhadeep Chakravarti from TCG Crest. So Shubhadeep, can you can share your screen?
Yes. Okay. Can you see, sir?
Yeah. So Shubhadeep will, we can see the screen. So Shubhadeep will tell us about non-reciprocal entanglement in cavity magnomechanics. And this is a 15-minute talk. So Shubhadeep, I'll tell you after 12 minutes are over.
Okay, sir.
Okay. So please go ahead.
Yeah. So first of all, I'd like to thank for giving me the opportunity. So I'll talk on entanglement in cavity magnetomechanical system, and I have planned my talk in the following manner. So first I talked about hybrid quantum system, and then I'll introduce this cavity magnomechanical systems to you, and then I'll show some recent results that realize non-reciprocity in cavity-based system, and then finally I'll talk about my results. So I will first like to show you this diagram, which essentially shows different type of hybrid quantum systems, but the x-axis is their coherence time and the y-axis is their intrinsic frequencies. So
Shubhadeep, so your volume sounds a little low. Is it possible to increase it a bit?
Is it okay now, sir? Is it okay?
It's better. Yes.
Okay. Okay, sir. So I was talking about this hybrid type of quantum systems where we basically couple to different type of quantum degrees of freedom, and that is due to the fact that these systems offer different advantages over the other for this problem specific job. So for example, when we want to transfer information, photons are a good choice, but when it comes to store the information, photon is not a good choice because of its high decoherence rate. So their mechanical oscillators come into the picture. So there are different class of hybrid quantum systems, and today I'm going to talk about cavity magnetic systems. But these systems can be essentially described by a two-mode model. So let us consider these two modes, A and B. They are coupled by this coupling strength G, and they are having their intrinsic decay rates gamma n and gamma b, and they're coupled to their respective reservoirs at temperature Ta and Tb respectively. So we can think of two different type of coupling. The first one is well known. This is known as the beam splitter type of coupling, which essentially let's say something like state swap between A and B. So this type of interaction is highly used in optomechanical systems to cool one of the mechanical oscillators. And I'd like to also show this type of interaction. This is the tumor splitting type of interaction, parametric amplification and used for creating entanglement or squeezing into the system. And when we need to study the dynamics of the system, we can resort to the Langevin type of equation. The first term is the Heisenberg equation, which is a commutator between the Hamiltonian and the operator. The second and third term are coming due to the decay rate of this mode, respective modes A and B, and this is the noise term that are coming from the reservoir system. Another physical quantities of relevance is here this cooperativity, which basically kills as G squared by gamma n and gamma b. So a high cooperativity means very, very greater than means that the system is in the strong coupling region. So whatever the system modes we are talking about, A and B, they are strongly coupled to each other. So next, I would like to show these type of systems. So magnetic system are something based on ferromagnetic samples, but we are going to study the interaction of these samples with a cavity field. So this is a macro cavity magnets. This type of system can be coupled to a superconducting qubit. They can be generalized in a on-chip type of systems. So basically, cavity or superconducting type of systems can be coupled to this magnetic type of system and can be studied to have a strong coherent interaction between these magnoid modes and the photonic modes. And then, so basically magnons means we are talking about the excitations of the spin waves. So when we place the ferromagnetic sample in a biased magnetic field, we will not talk about the individual spin anymore, rather we'll talk about its quantum spin wave, and the quantum of the spin wave is basically magnon. So the advantage of using these magnons is their frequency. So you can see here that the magnon frequency is plotted as a function of their external magnetic field, and we have a linear dependence between this frequency and the magnetic field. So the frequency goes like this. So we have a high tunability of the magnon frequency. And the quality factor is given like this, where this is the Landau-Lipschitz-Gilbert equation, where this M is the magnetization. So when you place the when you place this sample in a magnetic field, the magnetization pieces about the effective magnetic field. This is the torque term, and this is the damping term that is added phenomenologically over here. So this is the magnon. So when we try to couple this magnons to a cavity, we can think of the Hamiltonian like this. So the first term is an electromagnetic cavity. The second is the G-man energy, and the third one is the magnetic energy of the sample. So the effective Hamiltonian can be written like this. So A and M are respectively the annihilation and creation operators of, mode operators for these photons and magnons, and they couple to each other like a magnetic dipole type of interaction. So A dagger M plus A M dagger, this type of interaction. By this they are coupled. So what's the advantage here is that this coupling strength GM is very strong. So that type of coupling, the signature of strong coupling can be studied by studying the normal mode splitting, this figure. And I would like to also point that this coupling scales a square root of number of spins inside the sample. So basically we can achieve a strong coupling between the magnons and the cavity photons. So the two advantage of using this type of system is that the high tunability of their frequency and the strong coupling between this cavity and magnons can be achieved. Now let's come to the magnomechanical system. So this is a recent paper on Science that basically says that due to the magnetization, the sample deforms and generates a photonic mode into the system. So the coupling between the magnon is often mechanical radiation pressure type of coupling. So this is the nonlinear type of coupling talking about, and GMB is the coupling between the magnon and phonon mode. But please note that this coupling is very weak. This is in the millihertz range, so we can enhance the coupling by introducing mean field type of decomposition. So this magnetization in magnon mode is written like capital M plus small m. Here, capital M is the semi-classical amplitude of this, and by increasing this capital M value, we can effectively enhance the coupling between the magnon and the phonon mode. So in this experimental paper, using this type of magnetical system, they have shown cooperativity and high mechanical gain. So this is a recent experimental paper that I would like to show you. And now let's come to the another type of proposal based on this magnetical system. So J.S. Agarwal recently done this type of work where they are talking about the entanglement between these photons, magnons, and phonon modes in the magnetical system. Now, let us come to the fact how to achieve non-reciprocity in the system. So there is a recent proposal the spinning resonator. So that means we have a resonator that is rotating, and due to the rotation of this resonator, there is a frequency drag of the photonic mode. So this is basically car resonator, you can see, and with the spinning, there is a frequency shift of the photonic mode that is delta F, and that is given like this. So as this resonator rotates, so depending on the spin direction, so that means we are driving the system in a clockwise or counterclockwise direction, we can observe different type of effect. So here, a photon bunched statistics to photon anti-burst statistic type of transformation is shown depending on the direction of this propagation. And based on similar type of idea, phononic laser is also proposed in magnetic. So our work is motivated by this kind of works, which basically uses a spinning resonator and magnons type of thing coupled to each other. So what we are going to consider here, we are going to consider a whispering gallery cavity like this. We are having two modes. So one is clockwise mode and another one is counterclockwise mode. And these two modes are simultaneously coupled to the magnon mode. And there is a phononic mode associated with the magnon. So the first line of the Hamiltonian gives you the energy of this intrinsic mode. So this is the energy of the clockwise photonic mode. This is the counterclockwise photonic mode. This is the magnon energy, and this is the energy of the phononic mode. And this gives you the coupling. So this is the coupling between the magnon and photons, and this is the coupling between the magnons and phonons. Just look at the drive term. This is basically control the non-reciprocity here. So by driving this term means we are choosing the direction. So we can drive the system either in a clockwise direction. That means we are exciting the clockwise photonic mode without touching the counterclockwise mode. And we can do the reverse one also. We can excite the counterclockwise mode without touching the clockwise mode. But as we spin the resonator, as we just start rotating, so a shift can be introduced into the frequency. So now the clockwise mode is having frequency like omega CW plus delta F, and the counterclockwise mode is having a frequency like omega counterclockwise minus delta F. So depending on the spin direction, the two frequencies by an amount of plus delta F and minus delta F. So this is what I have shown here. That is the shift frequency with respect to the rotation speed. So if you increase the rotation speed, you can increase the shifting amount basically. So now let's talk how to have this mean field type of equation. So there is an explicit time dependence of the Hamiltonians. To get rid of this, we are going to a rotating frame where the Hamiltonian is defined like H0. And as we are going to the rotating frame, the detunings are introduced into the picture. So that this delta eta is the cavity detuning and delta m is the magnon detuning. So we are writing the Langevin type of equations. So here the first, this is the noise entering the photonic mode. So this is the noise that is coming due to the driving the cavities. This is the fluctuation of magnetic fields that is acting as a noise in the magnon mode, and this is the Brownian noise. So all these noises are stochastic. So the first moments are zero, and only second moments are there. And the enthermal is basically the thermal occupation of the phononic mode. And you can see that there is a driving term sitting over here. So you can, if you increase this E value, that means you can increase the amplitude of this A, and by increasing A, you can increase M and P also. So what I want to mean that we can achieve the mean field regime by tanking up the laser power by driving the cavity with a high amplitude laser. So that means we can have this type of mean field type of expansion where we are writing each operator as a summation of the mean fields or semi-classical large value plus small fluctuating term. And when we are doing this type of approximation, basically we are linearizing the system. So we can write the whole dynamics as a linearized equation where E is the vector of this fluctuation operators. All the fluctuations are written in terms of the quadrature position and momentum, something like this. And A is the bit matrix and N is the matrix of, it is the matrix of noises. So the noises that I was talking about here is the matrix of noises. So in diagram, linearized view, covariance matrix formalism becomes very useful. So we introduce the covariance matrix, which is defined like this, and the dynamics is governed by this type of equation. So when we are studying the steady state property, simply the left hand side becomes zero. So we are solving this equation to study all the relevant quantities that I'm going to show, mainly the entanglement part here, where D is the matrix of noise correlation. And now, as we are trying to calculate the entanglement, so we are using the partial transposition type here, which basically takes a transposition of one of the modes and study the logarithmic negativity to calculate the entanglement. And this is used to study tripartite entanglement in the system. So logarithmic negativity for bipartite entanglement, and this coentangle for studying the tripartite entanglement. So first, I'd like to show what happens here. So this is the entanglement. The first, let me show that say that this A, B, C respectively says the entanglement between photon and magnon, photon and phonon, and considering simultaneously these two modes, photon, magnon, and phonon. So these green curves are for stationary case. Stationary case means the cavity is not rotating here. So we cannot differentiate the entanglement gravity from the clockwise or counterclockwise. Both the cases gives you the same result. But when you drive the cavity in the clockwise and the cavity spin, you can see that for this range of delta, there is no entanglement between the magnons and the counterclockwise photon modes. That means a non-reciprocal type of behavior is achieved here. So by driving the cavity, for the parameters of delta for which the clockwise photon mode and magnon modes get entangled, there is no correlation between these two for the counterclockwise and magnon mode. Same thing happens here also. So this is giving you the entanglement between this photon.
Hi, Shubhadeep.
Yeah.
Shubhadeep. So 12 minutes are up now. So,
okay, sir. Last 2 minutes maybe.
Okay.
So this is the same thing for photon and phonon modes, and the last one is basically giving you the tripartite case. So all the cases we can see some type of non-reciprocal behavior by driving the cavity from a particular direction and entangling along that direction. Now to see the temperature dependence of this, so obviously when the temperature is increased, the effect is going to be deteriorated, and the same thing is happening here also. So this is, we have considered two temperatures, 0.3 Kelvin and 1 Kelvin. So for 1 Kelvin, there is no entanglement between the photon and magnon mode, but for these two cases, there is entanglement, but the non-reciprocity is still achieved. So we can say that non-reciprocity is temperature variation. And finally, I would like to consider this parameter. This is basically giving you the isolation parameter. So we are calculating the ratio if we drive the system in the clockwise direction with respect to if we drive the system from the counterclockwise direction. So you can see that depending on this delta, the ratio changes, and you can have a fair non-reciprocal behavior. Particularly for C, you can see that whenever delta is greater than 0, the entanglement by driving the clockwise mode dominates over the counterclockwise mode. So that basically gives you the non-reciprocal effect in cavity magnetomechanical system that is studied in terms of this entanglement calculation. We have plans to calculate other things also, mutual information and other information theoretic measure here. And we would like to extend this model by considering an extended version of more magnon system and having a complicated picture. So this is overall a summary of our work. So considering a magnomechanical system where the cavity is rotating, we have shown some non-reciprocal behavior, and that the non-reciprocal behavior is shown in terms of entanglement between the magnon and photon, magnon, phonon, and all the three modes simultaneously, magnon, photon, and phonon. So I'd like to end here, and I'd like to thank the organizer for giving me this opportunity.
Okay, thank you, Shubhadeep. Are there any questions? Okay. Doesn't look like there are any questions unless I'm missing something.
No, Diptimanda, I don't see any raised hands at least.
Yeah, okay. So, yeah, so if there are no more questions, then let's thank Shubhadeep for a very nice talk. And so this is the end of the session. And I'll turn it over to the organizers to make any announcements they want.
Sure. Thank you, Diptimanda, for chairing the session, and all the speakers for very interesting talks. So let's start in about 5 minutes. So it's 3:44, so about 3:50. It's fine, right? So we'll start at 3:50.
Okay.
So the speakers, thank you, Diptimanda.
Yeah.
So Nirmal, I'll make the speakers. I don't see Mukul, but let me make the Nirmal. Hi,
so I'm here. I'm here.
Yeah, I made you a co-host. Just try and share your screen.
Yeah. Thank you. Let me try.
Hey, Anamitra, can you hear me?
I'm yes, I can. Oh, Mukul.
Yeah.
I'll make you. But I don't. Why don't?
Yes,
You're called Isaac Pune. That's why I cannot. Okay, I see.
Oh yeah. I think I
No
used.
issues.
I think I used a
No issues.
different account. Yeah. Fine. Yeah.
That's it. Sure.
Hello.
So you are also course Nirmal. I can see your screen.
Okay, thank you.
Maybe you can go up and down a bit.
Sorry?
You could. Okay. You could have. I mean, it's fine. I guess. I was asking to do a slight transition to see, but that's okay.
Okay. Is it working?
Yeah. It's working.
Great. Thank you. So shall I stop sharing?
Yeah. For the moment, yes. Let's try if the others are there. Hi, Swarup. I mean, co-host. Maybe you can go ahead and check your screen once. Better.
Okay. Can you see?
Yes, I can see your. Maybe you can try full screen.
Okay. Yeah. Is it fine now?
Yeah. It's visible. Yeah, sure.
Fine.
Okay.
Then I stop sharing maybe.
Sure. So, Saurav Ghosh, I've made you a co-host. Can you hear me?
Yeah, so let me share my screen. Saurav?
Yeah, please.
Yeah.
Stop sharing.
I have stopped.
No, you didn't.
No, he has stopped. I think there is a delay.
No, I'm joking with him. Okay. Is it visible?
Yeah, absolutely.
It's visible. Yeah, it's visible.
So, thank you. So, how to sharing now? Yeah, that's fine.
Yeah, so there are 3 minutes.
Swarup?
Yes.
How are you doing?
I'm fine. How are you?
I'm doing great.
Hi, Mukula.
Hi, how are you? Hi, Saurav.
Hi.
Yeah, so a request, you should not allow anyone to ask questions.
Hello, where are you hiding?
Maybe I'll stop Saurav only asking from questions.
Okay. How is Nirmal? We all in the same.
Hey, I just went outside for a while.
Okay.
Yeah, it would be very interesting to chair a session with 3 of you guys.
It will be an interesting session. That is true. Yeah.
Good.
But I'm seeing all of you after a long time.
Yeah. I think next year things will be on offline, like physical mode.
I don't know. I mean, we were hoping that it happens as soon as possible. If not this one or something else.
Here we are back in physical.
Hey, Nirmal. How are you?
Hi.
Oh, after a long time.
How about you? Are you back in physical mode or online?
So we are in office, physical mode.
Yeah, office I can see, but the classes?
Classes, physical.
Okay, great.
So my class is physical. It just depends. My class I have only 4 students to teach.
Okay.
Very selective. You're very selective. It looks like. Even in teaching, you're very selective.
Okay. What?
I'm saying that even in teaching, you're very selective.
Yes.
Usually people are selective in choosing PhD students.
Is it?
Hi, Mukul. So it's 3. Sorry. I'm interjecting your friendly banter, but I'm sorry about that. So 3:50, maybe we can start.
3:50. Yeah, sure. Okay, so welcome all to the next session. And in this session, there will be 3 talks. Two of them would be on and around magnetism, and the last one would be on perovskite oxides. So I'm happy to share this session with all my old friends here. Okay, so first talk would be by Nirmal from IISER Bhopal, and he would be talking about magnetic quantum materials, which includes Rajba, like spin orbit coupling. So okay, so go ahead, Nirmal. I will give you a notice on 20 minutes. Okay, or so. Okay.
Thank you very much.
Sure.
I'll test sharing the screen first. Are my slides visible?
Not yet. Yes, now. Yes.
Okay, thank you. So at the outset, I thank the organizers for organizing this workshop once again and giving me an opportunity to present some of our recent works. As the title suggests, I'm going to talk about magnetic quantum materials. Now, quantum materials nowadays is a buzzword, therefore overused phrase. So I'm going to talk about heterostructures with Rajba-like spin orbit interaction that is useful for technology. And to this work, Joyita, Vivek, and Suman, these people have contributed. So let's start with quantum materials. Of course, every material that exhibits some quantum properties, essentially every material exhibits some kind of quantum property, so it's quantum material. But by the word quantum material, we typically mean some topologically non-trivial feature or some interesting spin orbit interaction that may include Rashba, Dresselhaus, or other similar kind of spin chiral spin orbit interaction. So if we talk about K dot P perturbation theory under certain inversion asymmetry, namely bulk and structure inversion asymmetry, we can write the Hamiltonian this way, where the first term is the free electron time like term, that is not the perturbation Hamiltonian, the H naught. And then comes the perturbation terms. Here it is the linear Rajba. This is cubic Rajba, that is cubic in K. Linear Dresselhaus and cubic Dresselhaus, that is also cubic in K. And if we solve this kind of a model, I don't want to solve everything together, parts of it, then what do we get? If we consider only structure inversion asymmetry, and if we consider only the linear in K terms, we get this kind of a Hamiltonian where the eigen's values look like this, considering H naught in it. And the eigenstates look like this. If we plot the eigenvalues in two-dimensional K space and the z-axis is energy axis, it looks like this, where at this point here, the red and blue bands touch. If I make a cross section, it looks like this. And usually in the band diagram that we see, we see this kind of feature for Rashba effect. Okay. Now, if we want to find the spin projections, there comes something interesting. The Sx, its expectation value turns out to be half sine phi, where phi is the polar angle in the 2D K space. Sy is minus half cos phi. By the way, we are talking about 2D K space because we are assuming electric field along the Kz direction, the Z direction. Therefore, the Rashba effect, the feature is found in Kx, Ky plane. And Sz becomes 0. So if we plot it on a contour of constant energy, we can see that the spins, they precess in a chiral fashion like this, and in the opposite sense for the inner one. Now, if we include cubic terms, then only for cubic Rashba effect, we can see that the eigenvalues look like this, hardly any difference. But if we look at the spin projection, there is a drastic difference. Here, unlike earlier, where we have found only one-fold rotational symmetry in the spin pattern, here we have three-fold rotational symmetry. Look at this, this, and this. You can see a three-fold rotational symmetry here. If we combine linear and cubic Rashba terms, we find a little bit of distortion, and only one-fold rotational symmetry of the spins is observed. Similarly, if we go for Dresselhaus Hamiltonian, the Dresselhaus Hamiltonian is given this way, which is similar to that of Rashba, but a little bit of difference. The eigenvalues turn out to be exactly the same. In place of alpha, here we have beta, that's all. No significant difference, but the eigenstates are very much different, and as a result, we have the projected spins looking like this. The pattern looks completely different. Similarly, if we include cubic terms, here the picture drastically changes. The eigenvalues and the projected spins, they look completely different. And if we include linear and cubic all terms, there is a bit more distortion, and this is the feature that we see in this case. So after discussing this, it's important to understand where actually these kind of effects could be important. How can we use this kind of effects? So if we have chiral spin arrangement, we can have spin orbit torque. What is spin orbit torque? For that, we require magnetic systems lacking inversion symmetry and some chiral spin orbit spin arrangement of chiral, which can be stabilized by sizable spin orbit interaction. And in that kind of a situation, we can have an electric current passing through the system and an electric field. They can tune the spin orbit torque so that the magnetic domains or the magnetic moments on every atom that can be rotated by generating this torque. So this feature can be used as spin manipulating device. That means we can have a certain kind of antiferromagnetic domain, and by passing a current, we can change the pattern of the spin texture of that domain. And that can be used for processors in computer as well as memory. And this phenomenon happens in very low energy, because spin orbit interaction has an extremely low energy and extremely high speed, that of terahertz. Therefore, it can be of very much use. And it also, the idea of antiferromagnetic spintronics also is of great promise, because it is robust against perturbation due to magnetic field. Antiferromagnets don't really get perturbed, and stray field also doesn't occur. And I already talked about the ultra fast operation. So what are the challenges remaining in front of us? The first challenge is very few potential materials are available, and my presentation would focus mainly on that part. The other things are uncontrolled size effects. We don't know exactly what size of the system gives what kind of effect of this. Magnetic textures are also very sensitive to layer thickness, and we have so far no way to control that. The growth condition, that is important, that plays a crucial role, and the transport properties in these textures, that's yet to be understood. That's important for realizing antiferromagnetic spintronics. Okay, let's come to the material front. Here we have first designed one heterostructure, the famous lanthanum aluminate strontium titanate heterostructure, and only strontium iridate layer has been sandwiched between them. Here is the strontium iridate layer that we have, and the structure turns out to be tilted. Now, if we take this, we find that these iridium atoms orient in antiferromagnetic fashion. I'm not showing the details of that. I'm directly going to the band structure that clearly shows a Rashba-like feature here. Here, as well as here, also the bands below. Now we will certainly focus on the bands that are near the Fermi level. And here, because it is a heterostructure, the growth direction is Z direction. We have Kx, Ky plane, Kx, Ky directions in the Brillouin zone, and Kz is missing because that is not a periodic direction. So if we plot the band as Kx, Ky and energy, the Z axis of this band is energy, we find this kind of a structure where this top part, if we zoom in, looks like two peaks here. Now, these bands are different from our earlier bands that I have shown from analytical modeling, because these are hole-like bands. So the bands are upside down. That part is fine. But then these two peaks here, that feature was not seen earlier. And if we take the contour here, that is, the bands are on this plane, this gray plane here, this makes this kind of a contour. So we can see elliptical bands here. And this is the feature. If we plot, if we bring the Fermi energy here, we can see the hole pockets here, and also electron pockets are present in these parts. These parts going below, they form electron pockets. And if we plot the Fermi contour looks like this. So it's important to analyze what is this two peak structure and what kind of interaction would lead to this kind of a feature in the constant energy contour. We therefore combine linear Rashba and linear Dresselhaus interactions, and by doing that we get the eigenvalues looking like this. If we get this kind of eigenvalues and if we plot them, we get this kind of a band structure for hole-like system. Two peaks are found, and if we intersect them, they look like this, but the contour looks a bit different. These are not elliptical contours, these are circular paths, and it's not along kx direction, it's along the diagonal in this plane, while the DFT result looked something like this. Here the two almost degenerate lines are because these are antiferromagnets, that we understand, but the structure, the feature is quite a bit different. Let's try to understand that. So we consider anisotropic effective mass. That means effective mass may be different along different directions, kx and ky direction. It may be different because our iridium oxide octahedra are tilted as shown here. And because the iridium oxide octahedra are tilted, the minimum structural unit cell that we require, that may be identified by this red square here in the plane, which is 45-degree rotated as opposed to this black square here, and the arm of black square was A, so this would be square root 2A. So we consider this kind of a cell and the corresponding crystal momenta axis we call Kx, capital Kx and capital Ky, and the capital Kx, capital Ky and small kx, small ky may be related by this kind of a transformation. It's a rotation. And using this kind of a transformation, that is capital Kx and capital Ky, if we write the anisotropic Rashba-Dresselhaus Hamiltonian, it takes this form with H naught equals the free electron term. But in the free electron term, we have different effective masses now, mx star and my star. If we do, if we take this and calculate the eigenvalues turn out to be this, and plotted in the band structure, it looks like this. And now we have elliptical bands because of anisotropic effective mass, and this major axis points along kx because of this rotational transformation that we have performed. Now, if we fit this our DFT results with this analytical model, we get this kind of fitting. 3 pictures of the fitting I have shown here, with mx star equals this much, my star equals this much, and the Rashba and Dresselhaus coefficients are given by this. So the Rashba and Dresselhaus coefficients are sizable, not huge, but it shows quite interesting effect in this system. And we can evaluate the constant energy contours by equating this eigenvalue to a constant energy and then evaluating the roots. The eigenstates can be evaluated like this. The plus minus, these are the eigenstates, and they are given by up and down spinors, with zeta being a complex number given by this here. And zeta star zeta equals 1. Now, if we want to calculate the projected spins, the expectation values of Sz, Sx, and Sy, Sz expectation value becomes 0. For Sx, it's this, and for Sy, it's something similar. And if we now plot that on the constant energy contour, we find this kind of a spin arrangement, chiral spin arrangement for this system. So this chiral spin arrangement, along with the embedded antiferromagnetism, may make it a useful system for antiferromagnetic spintronics. And we find something else interesting here. In this material, we have iridium atoms here that are that have very pronounced spin-orbit interaction, and there are many titanium atoms that normally have almost no spin-orbit interaction. But because of the proximity to iridium, we can see that these titanium bands here, these 4 bands, the titanium bands, they show sizable Rashba kind of splitting. And we can see that these bands, the corresponding charge density, although primarily on titanium, also spills over iridium atoms a bit. Therefore, the hybridization of iridium and titanium, that induces Rashba-like interaction in titanium bands. And this gives us an idea. We consider another heterostructure, barium manganate and potassium tantalate. Here is a depiction of that heterostructure. The in between this part is barium manganate. These are manganese atoms here. So barium manganate is usually not stable in cubic structure. It prefers hexagonal structure, but if we can deposit it on cubic potassium tantalate, it can be stable. And tantalum has very strong spin-orbit interaction, although in this compound, potassium tantalate, tantalum has 5+ oxidation state, therefore no 5d electron. But when we make this heterostructure, manganese comes in proximity with tantalum, it shows Rashba effect in many of its bands, the manganese bands. The tantalum bands, of course, retain Rashba effect. That's something trivial. That's not something we are mentioning here. But the manganese bands are near the Fermi energy. Tantalum bands are far away from the Fermi energy. And the manganese bands show Rashba interaction, also antiferromagnetism. So here is the 3D band, a pair of 3D bands that show Rashba-like interaction. And here we can see the constant energy contours as well as the projected spins, not from any model, rather directly from the DFT calculation. So we can see here the spins presses, but it doesn't presses according to whatever we have seen earlier in the theoretical description. This is something different, somewhat different. So it may be some other kind of mixture of linear and cubic Rashba and Dresselhaus terms, or maybe some other terms, because Rashba and Dresselhaus terms that we have arrived at is under certain approximation. That means only certain kind of inversion asymmetry we have considered. For other kind of inversion asymmetry, there can be other kind of terms involved. And this is what we find from our DFT calculation. We have also calculated for potassium tantalate surface. And for the surface, we find 2 different kind of bands. One kind of band shows this kind of interaction. Another kind shows this kind of interaction. Of course, this second kind is cut off so that you can see this red and blue bands touching here at this point. And the corresponding contours and spin textures look like this. So we can clearly see there is a chiral spin arrangement. In the first 4 pictures here, we have shown the spins from different energy bands. And here, these are from very close to this constant energy contour. That constant energy that we have for the contour, we have taken that. So here, these things, these bands and the spin arrangements kind of suggests that this possibly has a significant Dresselhaus component and also cubic terms involved in it. That's what we find from whatever we have seen earlier. We have also studied another hexagonal compound, manganese telluride. And in this manganese telluride, we find Rashba kind of interaction. This point where these two bands, red and blue, touch, that is the high symmetry K point in the hexagonal system, hexagonal Brillouin zone. And the corresponding band contours, constant energy contours, look like this. The projected spins, again from DFT calculation, not from any model, they look like this. So we can see that there is possibly an axis like this about which the spins flip. The blue spins take opposite sign and the red spins also take opposite sign when they cross this line that I have drawn. So I have here shown some different combinations of linear and cubic Rashba and Dresselhaus terms. These are some constant energy contours that we can get. Also, many other possibilities are there. And this brings me to the summary of this work. Here we have shown that chiral spin arrangements are useful for spin orbit torque, and that spin orbit torque is going to help us in developing antiferromagnetic spintronics technology. Rashba, Dresselhaus, and other similar interactions are important for realizing spin orbit torque. Here we have shown certain ways of designing heterostructures where we can host antiferromagnetism as well as Rashba, Dresselhaus, or similar kind of chiral spin arrangement. And here mentioning something is very important, that although we have seen that so far in the literature, many people have just seen two split bands in momentum space and called it Rashba. When we are talking about spin orbit torque and we are going to utilize it for some device, it is very important to find out exactly what kind of interaction it is and how the chiral spins behave in that system. Therefore, this kind of analytical study and numerical study, both doing both together, that's very important. And we have seen that surfaces and interfaces can be designed to host this kind of features, that is Rashba Dresselhaus interaction as well as antiferromagnetism. We have designed heterostructure based on proximity effect and projected spins from density functional theory results. And also our analytical models verify the type of interactions that we are talking about. Okay, this brings me to the end. Thank you for your attention, and I thank HPC facility of IISER Bhopal and ACRB and IISER Bhopal overall for the infrastructure and funds. Thank you.
Great. So Nirmal, thank you very much for a nice talk. So now the floor is open for question. Yes, Amrita, go ahead.
Nirmal, so can you just clarify, like, if there is some kind of dipole effect that you see, or do you have to take into account of that?
Dipole effect in what sense?
So dipole corrections should be there, no? So because your material should be polar material also, right?
Right, the material is polar. For example, this one, here the lanthanum aluminate part is polar and the other parts are non-polar. So that leads to a charge transfer at the interface, and so here every constituent material in here, those are insulators. But when we have this kind of heterostructure formed, because one part is polar and the other parts are non-polar, there is a charge transfer at the interface, and DFT takes care of this charge transfer quite well.
So in generally, so they also, incorporate some dipolar corrections. So in this type of material, so that's why I was just asking, like, have you also taken into account of those dipole corrections?
I guess because the interface is becoming conducting here, that correction is automatically taken care of.
Okay. Okay, fine. And all these structures are completely relaxed, or like, you know,
Yeah, these are completely relaxed.
Okay, no selective dynamics or anything.
No selective. No. It's completely relaxed also comes with one rider here for this one as well as this one, the YIMQCMT2021 KTA03. Here we have taken the in-plane lattice constant in AB plane, the same as the substrate. Here the substrate is potassium tantalate, and here the substrate is strontium titanate. So after freezing the in-plane lattice constant A and B for the substrate, we have allowed relaxation of every atom and the lattice constant along C direction.
Okay, so we can move to the next question. Please unmute yourself and ask. Yeah.
Hi, this is Ashish. So Nirmal, it's a nice talk. I have one question that this this Raspa tessellate or the cubic Raspa. So did you means explain with the symmetry of your 2D structure that which term will survive in the cubic case or whatever there? Because in principle, if you try to fit to a band structure, then that actually follows the symmetry. So the cubic form will change with the symmetry. So what kind of symmetry you expect in this case, like D to D, or because it's a cubic, right? So it's a plane is basically your square like.
Yeah, thank you for the question. This is possibly the most interesting question that we are trying to address. So whatever we understand so far, I can share that with you. Here, so it's about Rashba is about structure inversion asymmetry, and Dresselhaus comes from bulk inversion asymmetry. And linear and cubic terms are present in both cases. The cubic term is often suppressed because when we are looking at small k limit where the Rashba and Dresselhaus effect are visible, cubic terms, unless the coefficient is very large, cubic terms contribute very little in there. So the symmetry question comes whether it will be a Rashba kind of interaction or a Dresselhaus kind of interaction or both. Now, when we make this kind of a heterostructure, because of the heterostructure itself and the tilts in the octahedra, we can see that all kind of inversion symmetries are broken. Therefore, Rashba and Dresselhaus, they coexist and give this kind of picture here that we can explain from our model, including both terms. And their contribution is also quite similar. If you see the alpha and beta values here, they are sort of comparable.
Oh, okay. Thank you.
Okay, so I have one very short question, Nirmal. So how critical is the thickness of your sandwiched material in the middle? Here in this, in this one is quite big, I understand. But in your next superstructure that you had used in this YIMN031, so is it very critical? I mean, your thickness.
The thickness. So here, let me first go to the thickness in this case. Here we have the strontium titanate part. That's quite thick. This part is strontium titanate part, which is supposed to act as a substrate in real material. Here for simulation, we have simulated it like this. And then strontium iridate part is only 1 unit cell.
Okay.
Not more. Strontium iridate is 1 unit cell because in that limit or very small thickness limit, maybe up to 3 unit cell, it shows antiferromagnetic insulating feature, more antiferromagnetic Mott insulator. If we go for a thicker strontium iridate, it becomes a non-magnetic bad metal, which is useless for our context.
Nice. Okay.
And
Great.
this strontium titanate part is supposed to be a substrate. Therefore, this can be very thick. There is no problem with that.
Okay. Thank you, Nirmal.
So Mukulda, if you do not mind me asking, so can I ask a very small question, like last one?
Yeah, please go ahead very quickly. We are already over time. Yeah.
Very quickly. So if that is a substrate, Nirmal, so shouldn't we have a vacuum layer somewhere, or it's not required?
No, here the heterostructure is constructed in such a way that, so we are not considering any surface effect. Here we have constructed the heterostructure, this superlattice we can say, in such a way that if we consider very thick layers, a very thick substrate and substantially thick top layer also of lanthanum aluminate, then the whatever charge transfer we expect at the interface, exactly same amount of charge transfer is happening.
Okay.
So this is a trick that many people have used so far to make the calculations tractable.
Okay, fine. Thank you.
Yeah. Okay. So let us thank Nirmal for a very nice presentation. And we should quickly move to the next talk by Shahrukh from Bennett University, and he will be talking about magnetism in low dimension. Yeah.
My screen is visible.
So please go ahead. Yeah.
My screen is visible. Okay. So thank you very much, the organizers, for giving me this opportunity to present our recent work. So I'm working in Bennett University, which is a relatively new university, and we have I'm giving a small introduction because many of you may not know about this university. So we have School of Engineering and Applied Science and School of Media, School of Law, School of Management. And in School of Engineering and Applied Science, we have Bio Department, Physics, Chemistry, Math. So okay, so with that introduction, so we have a small group here, and we're working mainly on strongly correlated materials from density functional theory approach, DFT plus U, and dynamic and mean field theory based approaches. So today I'll be talking in one of the areas which we are working in collaboration. We are experimenters collaborated in IIT Tirupati. So we'll be talking about low dimensional system. So here is the outline of my talk. I'll first give an brief overview of low dimensional field system, and then I will talk about about a weakly coupled dimer and the physics of weakly coupled dimer, where we'll talk about a little bit about the Bose-Einstein condensation. And third, I will talk about a particular system which we believe that exhibit a Bose-Einstein condensation, that is K2Ni MO2H. And before proceeding to the talk, let me acknowledge my collaborator for this work, Professor Koteswar Rao from IIT Tirupati, who did the experimental part of this work, and Dr. Benjamin, who is my former colleague in École Polytechnique, and now assistant professor in Sorbonne University of France. My cursor is moving forward. So let me start the talk by giving a very brief introduction to the low dimensional spin system. Low dimensional means it's low dimension in the spin state, which implies if you consider this Heisenberg model, and you have this exchange interaction between the nearest neighbor spin, Aik. Now, often what you see, although the material is in 3 dimensions, but the exchange interaction is strong along a particular direction, and we call 1D spin chain. And then also you can have a square spin arrangement, where the exchange interaction is basically confined to the plane. And out of plane, the exchange interaction is too small, so we can think of a square arrangement of the spin. So there can be also triangular lattice in the plane. And then another interesting set of materials is the spin dimers material, where you see you'll see that there are 2 neighboring spins, which is a very strong magnetic exchange interaction, where this the interdimer interactions are relatively weak. Now, these are some of the low dimensional spin system, and it has been discussed in literature quite in detail. So what we see in general in this kind of materials, that quantum fluctuations are very strong. Often magnetic fluctuations play a crucial role, and we also see many exotic phases like spin liquid phases, ground state, Bose-Einstein condensations, all these things we see in this material. So today I will be primarily concentrating on the spin dimer material. So let me discuss about the general scenario of the spin dimer. So here is a schematic of some of the spin in the plane. So as you can see, these two spins are interacting via an exchange interaction called J, and then we put another exchange interaction between the two diamonds that is called lambda J. Now, depending on the limit of the lambda, so for example, if lambda is 1, that means the two exchange interactions are quite almost equal or equal, then we have this square lattice antiferromagnetic in this region. And if lambda is small, then we go to the dimer limit, often called quickly coupled dimer, because this interaction is much smaller than this dimer exchange interaction. So these two spin couple very strongly, whether this dimer interact very with a relatively much smaller exchange interaction with the nearest neighbor dimers. So these are called weakly coupled dimers. And what has been observed is these weakly coupled dimers are quite interesting because they exhibit Bose-Einstein condensation. So, and the Bose-Einstein condensation, we can also, in a simple schematic picture, we can try to understand why these weakly coupled dimers can exhibit Bose-Einstein condensation. So as you can see that there are two spins. So if you do an addition of spin angular momentum, the two possible total spin state are S is equal to 0 and S is equal to 1. And so I'm basically discussing about the dimer itself. Let's for the time being, let's forget about the dimer interaction. So we have, let's say, dimer, and these two dimer couple. Then you have two possible states, S is equal to 0 ground state and S is equal to 1 triple excited state. Now, once we applied the field, as you know, due to the Zeeman splitting, this S is equal to 1 manifold will be split into 3 MS states, MS plus 1, 0, and minus 1. And at a critical phase, you have actually degeneracy between, the MS is equal to plus 1 state and S is equal to 0 state. So 1, 1 and 0, 0 states are degenerate. And what is observed just below this critical field at a finite temperature, you often observe Bose-Einstein condensation of Sz is equal to plus 1 triplet. So that is actually has been observed in many systems, and it extensively studied for spin half dimer. Here are some of the examples you can go through. Now, this is for spin half dimer, but if you look at spin one dimer, the scenario becomes even more interesting, because in spin one dimer, what you have spin 1 in every side. That means there are two S is equal to 1 spin. Now, if there are two S is equal to 1 spin, if you do addition of spin angular quantum number, you have 3 spin states, right? S is equal to, because it's S1 plus S2 to S1 minus S2. So you have S is equal to 0 to capital S is equal to 2. So you have 3 states. Capital S is equal to 0, capital S1, and capital S2. And why it is more interesting, because you can see now once you apply the magnetic field and keep on increasing the magnetic field, this S is equal to 1 will be split into 3 MS states, plus 1, 0, and minus 1. For this S is equal to 3, this will be split into 5 states. MS is equal to plus 2, plus 1, 0, minus 1, and minus 2. And what you observe here also, that you see there are two critical fields. In a smaller field at SC1, there is a degeneration between MS is equal to plus 1 and S is equal to 0, MS is equal to 0 state. And then at a larger field, you have another degeneration of MS is equal to plus 2 state with the S is equal to 0. So there are possibilities that there is, in addition to the stippler condensation, you can also have quintuplum condensation at a higher magnetic field. So that's why this spin one dimer could be very, very interesting. But what you also see in the literature, there are very few examples in real materials which exhibit this kind of condensation. One of the examples we found is BMN2Y. Okay, so that's why we were thinking that whether we can find some spin one dimer which can easily couple with the nearest dimer. And with that search, we find out our experimental collaborator, Dr. Koteswar Rao, who find out this K2NI-MO2OH system. And I will mainly talk about our results, which will be, we are preparing to submit it. It's our recent work, so any suggestions are very much welcome. So here in this system, we will try to find out whether this system can exhibit Bose-Einstein condensation. So the approach we will follow, first I will try to make sure from our density functional theory calculations that is it really a spin-on dimer or not? And then we'll see whether what is the strength of the weak the inter-dimer coupling, whether it's in the weak limit or not. That is something we'll try to find out from density functional theory, and this will do both from the electronic model as well from the spin model. And once we estimate the magnetic exchange interaction from DFT plus U approach, because these are, as you can see, the nickel is a correlated ion, so we'll use DFT plus U approach to estimate the exchange interaction. And once we estimate the exchange interaction, we'll use those exchange interactions to compute some of the experimental quantity like magnetic susceptibility, magnetization versus field, and we'll try to see whether our parameterization for our estimated exchange parameters are in agreement with the experimental data or not. So in that way, we'll try to find out the real or the correct set of exchange parameters. And once we have a correct set of parameters, then we'll go to a hardcore bosons model, where with that model we'll try to understand whether this system is exhibit Bose-Einstein condensation or not. And this third part has been done by my collaborator, Professor Benjamin in Soviet University. Okay, so let us first start with the first part, which is it really a spin-on dimer or not? So we'll try to just understand from the structural point of view. So this is the crystal structure of this material. So briefly, if you look at this structure, we have a nickel layer in the AC plane, and this interplanar distance is quite large. So it's an almost planar structure. So if I just focus on this AC plane, what you see, you have these nickels, which are two nickels which are very close by, and there are these nickel are spreaded in the completely AC plane. So it's very, very nice, beautiful structure, as you can see in the AC plane. And if we look at the distance and also the corresponding magnetic exchange interaction, what we see that the distance between these two nickel, which we believe that form a structural dimer, 3.0 angstrom, and the distance between the dimer is relatively large, 5.4 angstrom along the a-axis, and in this one is 5.6 angstrom. So we'll mark this exchange in the dimer as J0, and then the inter-dimer interaction will mark as like J1 along a-axis, and this is J2, and then there is a relatively larger distance J3. But even from the distance point of view, we can see that these two nickels are very, very close, so they really form a structural dimer, and the nearest neighbor distance between the dimers are quite large, 5.4 and 5.6. So we started to understand electronically first by looking at the non-spin polarized electronic structure. So whether it's really they form a dimer or not, although from structurally, as I mentioned, structurally they form the dimer. So what we did, we calculate the non-spin polarized electronic structure, and I want your focus to be near the Fermi level. So nickel in D8 configuration, what we see from the density of state, that T2T state, which can take 6 electrons, are completely occupied, or this is non-spin polarized. So you see that there is half-filled EG state. Now, this half-filled, there are 4 nickel in the unit cell. So we observe there are 8 bands near the Fermi level, which we have treated here, Uni 180, which we'll discuss. So what you see, this EG bands possibly the main bands which will contribute to the magnetism. So that's the reason we wanted to see what's the hopping strain between this EG state, and we also wanted to see the nature of the fad bands of the EG state. So what we did, we plotted the fad band near the Fermi level, and as you can see, there are 2 EG bands, and the fad bands are very interesting in the sense, you see one of the EG bands clearly show a bonding anti-bonding kind of splitting. You see, this is one of the EG band, and then there is there's 2 EG here and 2 EG here, because there are 4 nickel. So you see, these are really kind of bonding anti-bonding states, as you see in a molecular orbital, right? So that's kind of splitting is quite visible. Or for EG2 also we see some splitting at some of the K points, but I mean the relative splitting is smaller than the splitting in the EG1 state, and that will be clearly see if when we calculate the hopping parameters. So then what we did next phase, we took those 8 bands and fitted with using the 1N90 technique. We fitted those bands and tried to calculate the hopping parameters within the dimer and also the inter-dimer. Now, what these hopping parameters indicate, as you can see from this table, that the hopping chain within the dimer, this is this T is quite large. This 201 in one of the orbitals. This is milliardsfold. While the other hopping chains are relatively small. So this itself, from the non-spheroid polarized structure, tells that these two orbitals really hybridize a lot. This is one because and also from a structural point of view, you can understand because this EG1 orbital is basically directed towards the AXis, so that's the reason it's happening. Okay, so with that, but also you know that in a one orbital model, the exchange interaction is proportional to T squared by U. So from our Hawking calculation, even we can indicate that there is a strong dimer formation or that there is weak inter-dimer coupling. So that is something we can see with this calculation also indicate. But going ahead, we wanted to estimate those exchange interaction from spin polarized calculation. So that's why you go to the second part. So we already have we know that this dimer is strong dimer with weak inter-dimer coupling from the Hawking, but we wanted to have a quantitative estimation of those exchange interaction, and that's why you perform GST plus U calculation and estimated those exchange interactions and try to explain the experimental data based on those parameters. So here, bring me to this magnetic exchange value from LSTA plus U for different U values. As you can see, as expected, and as I mentioned, that basically exchange interaction is inversely proportional to the Hubbard U. So as you increase the Hubbard U value, the J0, which is the exchange interaction in the dimer, inside the dimer, and J1, J2, and J3 are the inter-dimer couplings, the various inter-dimer coupling which you're interested in. So we basically map this GST plus U energies and use the to Heisenberg spin model and use the magnetic force theorem to compute this exchange interaction. What we see that exchange interaction, of course, gradually decreases as you increase the U value. But most importantly, what we see in all this calculation, with respect to value of U, that exchange interaction J0 is very, very strong. You see, these are very, very strong. Whether the inter-dimer coupling are quite weak. So this is very interesting in the sense that we have the correct material, that we have strong dimer coupling and weak inter-dimer coupling. And that is kind of materials we are looking for. So, and then also from our earlier calculation of CRPA, Hubbard U calculation using CRPA, we know that the U is equal to 6 dB is quite a good value for nickel 2+ state. So that's why we take that Hubbard U and these parameters for further understanding the magnetic data. So this is the parameter we'll be using to understand the magnetism of this material later on. So this 38.98 is J0 and then the 2.2, 1.7 and -1. Okay, so with that parameterization, if you just look at the dimer, so for example, if you just look at this dimer interaction and forget about the inter-dimer coupling, so in a dimer physics, you can, I mean, we can do a small statistical ensemble, and from that we can calculate the susceptibility. So that is my chi0 based on the J0 value, and then I can take this inter-dimer coupling, which is quite small, in a mean field manner, and I can calculate the total susceptibility chi. So that's what we did and plotted here as a function of temperature using the statistical. And as you see that the experimental curve is this dotted black one. So you see dimer fit keep quite a good agreement, but a little bit shifted from the intensity a little bit higher. But then as soon as you put this mean field approach and bring the inter-dimer coupling, that discrepancy goes away, and you have a very good agreement between the experimental susceptibility and the theoretical one. So this indicates that we have a good set of parameters. And further, we also did quantum Monte Carlo calculations with those parameters, and we found that the mean field calculus and the quantum Monte Carlo calculations are quite in good agreement. So if this magnetic susceptibility data and a good agreement with the experiment itself indicate that we have a very good set of exchange interaction parameters from GST plus U approach. So further, what we did, so as I discussed at the beginning, that so if you just consider dimer and forget about the inter-dimer coupling, you have two transitions. One is J0 by G mu B from S is equal to 0. So it's transition from 0, 0 to 1, 1 state, and then there is another transition to the quantiform state, the 2-2 state. So that's something we know. So that means if we apply field and try to see the magnetic saturation, as you can see, this is M by M saturation, because the final value has all the spins to be parallel. We consider as a saturated value as 1, so that don't get confused, because while all the parallel, there are spin values 2, but we have plotted here M by M saturation. So that's why we have 0.5 and 1 value. So if we don't consider any interdimensional coupling, we should expect a sharp jump at this value from singlet to triple state, and then at higher value we should again see a state sharp jump. But because of this interdimensional coupling, we see here there is a slope, and this is important because this is something also we observe experimentally, that there is a slope here, and so interdimensional coupling should be considered, although they are small. So that's what we see from the mean field approach. That mean field approach give us the M versus H plot quite nicely, but then we wanted to do quantum Monte Carlo with a more sophisticated way, including the temperature effect. So we do quantum Monte Carlo at 1.5 Kelvin, and because of the temperature, there will be a little bit broadening. I mean, sort of the slope will be changed a little bit, and that's what we see. That the slope is, but we basically saw that quantum Monte Carlo result and mean field results are very close to each other if you can decrease the temperature in a relatively low value. So what we see that the agreement is quite nice. Of course, it's not on top of each other, but there is quite a good agreement. So again, this understanding the susceptibility data, understanding the magnetization versus H plot, all these things essentially tell us that we have actually good set of exchange parameters from Day3 plus U, and we can go ahead with that. So far we have that's the thing we have observed. So now, as I discussed at the beginning, that now this is the part which would be interesting to understand the condition. This is one part, and this is another part, because below this critical magnetic field, we should, at a very low temperature, we should expect a condensation. And to understand that, so what we did, that we go to the last part of the calculation. As I told, this is done by one of my collaborator. And what we did here, we basically, starting from the spin model, we had this parameter. We know J0, we know J1. We basically, spin model was mapped to a sort of a hardcore boson model. And the primary philosophy of this model is that basically each dimer is mapped to a lattice site. That means this is one of the lattice sites. Now, this lattice site is empty. Yeah.
Saurabh, you have only 4 minutes left, including.
Yeah, almost. I'm almost done. So another one or two slides. Yeah.
Sure.
So you see, if this site is empty, if the dimer is H is equal to 0 state, that means a singlet state, and this site will be occupied if dimer is in triple state. That means H is equal to 1 state. So we are primarily concentrating at the first slope of the M versus H curve. So then, if you map this spin model to this hardcore boson model, what you have? So you have different sites, and this T1, V1, and T2, V2 are related to the this interdimer exchange interaction. So you see, within this site, we have included all this exchange interaction as well as the magnetic field effect, and then we have the T1, V1, T2, V2, all are related to this J1, J2, J3. So this is how the mapping is done. So site has a maximum occupation of can host maximum one boson when it is in the triple state. So this is the Hamiltonian we got by doing this transforming the spin model to the hardcore boson model. And just I wanted to point out this chemical potential here is in this boson model is equivalent. I mean, it's not equivalent, but it's related to the applying magnetic field and also J0 in the spin model. So that's why we can you basically use this to relate the boson model to the spin model. Finally, we will plot the sum of the quantities as a function of magnetic field. So this is where we vary. Okay, so this is the primary philosophy of this model. And so what we show as this is the thing that which I already discussed. So we have this QMC calculation, and we try to concentrate very near to this critical field. And as you can see here, we have plotted near this 23 to 27 magnetic field. So this is mu naught H. I follow the axis here. So this is mu naught H axis. So this is the magnetic field from 23 to 27, and this is the spin stiffness as well as the occupation number. Now, as you can see, as I told, if the bosons are in a singlet state, that means there is no occupancy. If it is in triple state, then it is 1. So that's what you see at around 23.5 to 24, the occupation starts growing up, and then you have a full occupied at this one. And also we have a finite stiffness at very low temperature. So we observe that the critical temperature is 0.2 Kelvin, and this is so by this the finite stiffness indicates that there is a that condensation happening at this below this 0.2 Kelvin, which we have plotted T is equal to 0.1 Kelvin only. So and in this magnetic field region, so we basically confirm that the system exhibit post-Einstein condensations below T is equal to 0.2 Kelvin. So here is a summary. We first discussed about the electronic model, and we found the strong diamond hopping, and then we discussed about the spin model, and to understand the magnetism versus magnetic susceptibility and magnetization versus field plot. And finally, we map this spin model to hardcore boson model to understand the critical conditions with the field and the critical temperature for post-Einstein condensation. And thank you very much for your attention. Yeah. So, Gulam.
So thank you, Shaurabh, for an excellent talk. So now the floor is open for question, and we can have a very short 1 or 2 questions only. Yeah, please go ahead, unmute yourself and ask. So is there any? Yeah.
Thank you for the presentation. Since there is no more, no hands, I do not see any. That's why I'm asking. So can you just comment on the U parameter? You went on over it very quickly. So ultimately, did you just calculate the U, or you found it from some experiment?
No. So the point is so easy. We have the earlier did calculation for nickel oxide. And this is the paper I was referring to. For nickel oxide, we did U calculation. It was close to 6 dB. But for this system, because of the technical reason, we could not calculate it because it's a big system, and doing a CRPA calculation for such a big system is not very easy. So that's why we took that U value for nickel oxide, which has also 2+ state. Here also it is 2+ state. So that's how we try to justify the Haber U.
Okay.
And also you see. Also, the point is, you see, with this parameterization, we could estimate the magnetic susceptibility as well as the magnetization versus H plot very nicely. So we believe that our DFT plus U estimation and the model calculations are in line.
Okay, fine.
Shaurabh, along that line, Shaurabh, since your requirement is the ratio of J0 and J1, J2, whatever. So even if you vary U, let's say I don't know what is the corrective, okay? And if I go below 6 eV, okay, your requirement is still there, right? So you will, so will you predict a qualitatively same physics there?
Yeah. So the point is, you see, from the susceptibility, you can also see this position of this broad arm, which is a very typical feature of low dynamics in the material, is around 47 Kelvin. This particular arm. Now, if you, for example, if you reduce the J0 value to 30 Kelvin or 25 Kelvin, which you expect if you increase the U, right? So let's say U is equal to 8, you take, and then you will see that this position of the peak is not coming at the right.
No, I understand that. Maybe there would be a quantitative problem, but qualitatively you would expect the same physics there, right?
Yeah, absolutely. Because so after that, the kind of calculus we have done, for example, is
model. Just
the relative values are important.
Yeah. Okay.
In fact, I did not mention, but I think since we are not considering any other, we are only using the symmetric extreme, that we are not using magnetic anisotropy or anything. We actually also expect the same physics in the higher field, where the quantifiable condensation happens.
Right. Okay. So let's thank Sharup again for an excellent talk and move to the last talk of the session and the day by Saurabh Ghosh. Saurabh is in SRM Institute, and he will be talking about cation order magnetic perovskite oxides. So Saurabh, please go ahead, and I will give you a notice around 20-21 minutes. Okay.
Sorry, is my screen visible?
Yes, it is.
Yeah.
Yes, it is.
Okay.
Please go ahead. Yeah.
Thank you, Mukulda, for nice introduction. So I'll a little bit change my title of my presentation. So the title of my presentation is Insights of Cation Ordering in Double Perovskites from First Principle Calculations and Machine Learning. So here in this talk, we are going to try to understand that what really decides a clear cation ordering in double perovskites, and can only DFT give you an insight of it, or you need to go beyond DFT and you need to adopt new methodology for that. So with that, this is my So this is the outline of my talk. So first I will briefly go through that why we are interested in cation ordering, and then I briefly mention the methodology that we used in this project work. And basically, density functional theory-based calculation has been performed to get the geometry and the other magnetic properties. And then we adopted machine learning technique to understand this cation ordering in more in depth. So we'll be mainly focusing on this cation ordered magnetic double perovskite oxides, A prime, BB prime, O6. And then from the first principle calculations, we'll get an insight of how we can achieve clear cation ordering. So and we'll be following these different relative energies between 3D, 5D systems. We will also consider the disorder effects in double perovskites, and also we'll calculate the formation energies to predict the actual chemical paths that you basically get it from the experiments. And then we'll discuss electronic structure. And then in the last part of my talk, I will basically talk about how machine learning can give you an insight of understanding regarding the cation ordering. Then a summary and conclusion, and then acknowledgements. So with that, so why we are interested in cation ordering? So this is in the left hand side. Here you have so in the left hand side. So in this left hand side, you have a high temperature, high symmetry structure of AbO3 perovskite oxides. So you can see. So here this is a cubic structure at high symmetry, and it's a very simple structure. You have A cations at the corner of the cube, and at the center we have a B cation, and it forms basically a BO6 octahedra. Now, if we change the relative size between A and B, then these octahedras are going to be tilt and rotate. And because this A cation is in cubic octahedral positions, so we can imagine that if you keep increasing the size of the A cation, then these octahedras are going to be very rigid. But if we consider smaller A cations, then these octahedras are going to be tilt and rotate. And in experimental or in compositional space, in structural and compositional space, these PNM structures are the most common in perovskites, where you have this A minus C plus rotation pattern. I'll come to that. So now if you do a phonon calculation in the high symmetry structure, we'll get imaginary phonon modes. And if you freeze in individual imaginary phonon modes, then it will lead to intermediate phases, right? So now if we perform a phonon calculation in simple, say, lanthanum ferrite cubic structure, then we'll get these three main modes, okay? So one is the in-phase rotations, that is the octahedras are rotating in phase in a plane. And in glacial rotation, you say it A minus C plus. And then you have these tilt distortions, octahedra tilting along A or B. And this in glacial rotation, you define this as A minus C0. and then you have this Q antiferroelectric A cation displacement. In here, basically two AO layers, they move in opposite direction. You can see that it is arrow that one AO layer is moving in positive x direction, then another AO layer is moving in the opposite direction. Now, if we write down the Landau free energy expansion, then there is a trilinear coupling between this rotation, tilt, and antiferroelectric A side displacement, and that basically drives the system more lower than any other competing structural phases. Now, why we are interested in this trilinear coupling? Because we can design ferroelectrics by using this trilinear coupling mechanism, which is called hybrid improper ferroelectricity. It's discovered in almost 10 years ago. So here we can really use this mechanism to design new ferroelectric materials where the bulk components are not ferroelectric at all. But however, if you make them superlattice or double perovskites, then you can induce ferroelectric property into the system. How? So in the left-hand side, this is simple PNMA. So it's lanthanum ferrite. And you can see the two cations are moving in the opposite direction. So if we calculate the layered polarization, then these two layers, then we will get this equal magnitude in the layered polarization. But however, these polarizations are aligned in the opposite direction. So there is an exact cancellation. And that's why lanthanum ferrite in PNMA structure is not ferroelectric. Is basically its total polarization is 0. However, if we can design this such a way, I don't know what's happening with this. Sorry, what this was. Is visible now? Yeah. Is it visible?
Yes, sure.
So now, if we can make, if we consider a superlattice of a lanthanum ferrite and yttrium ferrite, so lanthanum ferrite and yttrium ferrite superlattice, then you have two successive layers which are different cations. One is AO, another is A prime O. So now if you measure the layered polarization again by density functional theory, then you will get that there is a non-cancellation. So there will be a net polarization into the system. So this A1 by N superlattices, or you can say lanthanum yttrium Fe2O6 double perovskites can become ferroelectric. Now, I have a problem with this. I don't know why. Okay, 1 minute. Sorry. 1 minute. Now can you see it?
Yes, sure.
Okay, so now that's fine.
Yes, it's fine. Yeah.
Okay. So now there's a non-cancellation, and this non-cancellation gives you a layer polarization. However, I as mentioned, there's a trilinear coupling between rotation and tilt. So here, both rotation and tilt, they are the primary order parameter, and the polarization is the secondary order parameter. So in this plot, what I have seen here is you can see that there is if you change the rotation, then along this particular path, then you can switch the direction of the polarization, because rotation, if you change the sense of the rotation, then you basically change the direction of the polarization. But if you change the direct sense of the tilt, that is, you're going from a positive tilt to a negative tilt, then you can basically change both the direction of the polarization and magnetization, because the magnetization is related to the tilt distortion. So basically, that's why we're interested in cation ordering. So you can understand, if you invoke double perovskites, and we can be able to design materials where we have a perfect A-side cation ordering, then you can design new multiferroic materials. And that is the motivation of the present work. So with that, so now there is a challenge. So if you are talking about double perovskites, then you have two sublattices, A sublattice and B sublattice. And A sublattice can be ordered in 3 different ways. So layered, A sublattices can also order in 3 different ways, like layered, Roxel, and columnar. And B sublattices also can order in 3 different ways, layered, columnar, and Roxel. So you have total 9 different possibilities. So in the left-hand side, what I have shown is basically a representation where you can see that in the left-hand column, there is A sides are ordered. So A sides are layered order. So you can see the A sides are layered ordered, but in the first one, B sides are also layered order. In the second, A sites are layer ordered, but the B sites are in Roxol ordering. And in the last figure here, the A sites are ordered, A site ordered, and the B sites are columnar ordered. Similarly, you can have A sites and Roxol, B site X site Roxol, B site layer, then B site Roxol, B site columnar. Similarly, with A site columnar ordering, you can have B site layer, B site Roxol, and B site columnar. So total 9 different possibilities are here. But we are particularly interested in this A site layer ordering with the B site Roxol ordering. So this is now let's define this compositional space. So this is my disorder phase. So here we haven't involved any A site or B site ordering. Now now you can see in the first here, so we are involving B site Roxol ordering. So the cubic symmetry is PM3M. When we invoke B site Roxol ordering at the B site, then the space group lead to a PM3M. Similarly, when you introduce columnar ordering at the B site, it goes to P4/MM. And if you introduce this B site layer ordering, then it goes to a space group P4/MMM. Within that B site Roxol ordering, you can also now introduce A site ordering. So you can have 3 possibilities again: layer, A site columnar, and A site Roxol. And in this column is basically showing that where we have no distortion into the system. The system is perfectly, there is no rotation, no tilt, nothing. But if you introduce now this A-C plus distortion, then you can see some of the boxes are green and some of the boxes are not green. So the boxes which are green, they are basically represents a polar space group. That means with the combination of a particular A site ordering with a B site ordering, with a particular combination of the rotation, you can have different polar phases. So that is the analysis we did initially to get out that what are the possibilities of the polar phases. And then, as you mentioned, this is a cartoon of A prime, B prime, O6 double perovskites, and then A sites in the periodic table. It shows that you can have different kind of A site possibilities, B site possibilities. Mainly B site and B prime sites are mainly 3D, 4D, and 5D transitional metals. Now the question is that how to understand the relative stability between these phases. So here to mention, so you have 9 different orderings, and you have 4 magnetic orderings: ferromagnetic, then antiferromagnetic A, C, and G. So for one particular compound, you have to do 36 geometry optimization. Geometry optimization. And this geometry optimization, density of state calculation, magnetic calculations, all these calculations we have done by using density functional theory. Now, first let's try to understand the 3D system. That is, we have A prime, BB prime, O6, where your A site is sodium plus and B site is yttrium plus, yttrium 3 plus. So AMM prime, some of the oxidation state of the AMM prime should be +8, right? So in 3D system, generally you have similar charge states like manganese 4 plus, iron 4 plus, manganese 3 plus, manganese 3 plus, like that. So is more likely the AMM M prime will have the equal oxidation state. So we start with La2 manganese, nickel manganese O6. So here there is no A site cation ordering. So only B sites considering the ordering. So you can see here two very important notes that I want to make here. The colors represent B site ordering. So red means B site Roxol, cyan means B site columnar, black means B site layer. However, the symbols represent A site ordering. Star means Roxol ordering, square means columnar ordering, and layer circle means layer ordering. So if you consider the first one, where you don't have any A site ordering at all, only B site ordering, you can see these B site orderings form bands. Why I'm saying bands? Because you can see they are all the same color. So this Roxol, so B site Roxol orderings are well separated from the columnar and the layer ordering. And here also in between this B site Roxol ordering, there are these symbols. These symbols represents it's basically one symbol because there is no A site cation ordering, right? And these 4 symbols represents 4 different magnetic configurations. So from this ground state parent compound analysis, what we have found that these B sites BB prime ordering, they form in bands. Now we triggered the system. We have now started invoking the A-side cation ordering. So you can see the first example, lanthanum, yttrium, nickel manganese O6, where lanthanum and nickel both are +3 charge state. And you can understand that still that the band remains. However, A-sides are not giving a clear ordering. Okay. Then we tried to do doping electron. So we took the combination C over yttrium. Then still this band disappears. This band disappears. We tried whole doping. Still, we didn't get any clear ordering. Then we tried sodium, yttrium, nickel manganese O6. Then still there is no clear ordering. So these bands overlap. And that means for the 3D system, you should not have in both A-side and B-side ordering. And that is basically true. There is no report of both A-side and B-side ordering in a 3D system. Now that makes us to go beyond the 3D and we invoke the 3D 5D system. So here you can see we have considered these 12 3D combinations at the A prime, BB prime, MM prime O6, where sodium is +1, yttrium is +3. And so my M and M prime summation is again +8. But now here your M and M prime oxidation state can be separated. So in these particular combinations, that what we have calculated, we have considered this manganese, iron, cobalt, nickel as 3D and tungsten, rhenium, osmium as 5D. And we have found all these combinations, we generally get +2 +6 charge oxidation combination. That is, my 3D is +2, my 5D is +6, except this sodium, yttrium, iron, osmium, O6 compound. So that means that clear ordering can be achieved for the 3D 5D systems, and you can see the bands are very well separated. Now, the question then there are other many effects that can basically very important for your clear ordering. So what we are trying to achieve is A-side cation ordering with the B-side Roxol ordering. So we have disorder is one of the important features that we should consider. So here we have considered the diode. We have performed the quasi-random analysis, and we have calculated the disorder A-side disorder structures. So using this method is developed by Alex Zunger, and we use this method. We have generated A-side disorder structures, and we compared the energies of the A-side disorder structures with the ordered 3D 5D systems, and we have found that this is again this A-side layer, B-side rock salt ordering for the 3D 5D systems. They are stable with the disorder as well. Now, next important point is that what about the formation energy? So I am saying that my 3D 5D system will be A-side layer ordering and the B-side rock salt ordering, but we experimentally need to form them. So now we calculate the formation energies of this A prime, MM prime, O6. We've calculated the formation energy with respect to the binary oxides and also with respect to the perovskite oxides, right? So like A prime, MM prime, O6, then it can decompose into AM, O3, AM prime, O3, A prime, MO3, like that. So we calculate the formation energies with respect to decomposition of the binary oxides and the ternary oxides and the perovskite oxides, and we have found that both the cases the formation energies are negative. That means all the compounds can be formed, but this is misleading. So some of the compounds may not be formed because experimentally all the compounds are not reported to be formed. Then what we did, we have found out a very method. It's the first time we have introduced this method in double perovskite. So what we have calculated here, we have calculated the actual true chemical energy pathways that what we'll expect from the experiments. So what we considered, for material informatics, we have a pool of possible binary oxides, ternary oxides, combining all the components. And what we did is basically this is my reaction pathways, G equals to some number I, Xi, Fi, where G is the total reaction sequence. And then what we did, we basically minimize this reaction equation pathways with a constant, with this particular constant. That basically will give me all the possible reaction pathways that a particular double perovskite can decompose. And we found that there are many possible equations can be possible for a particular decomposition of a double perovskites. And for this particular compound, like sodium, yttrium, cobalt WO6, I have here noted only 4 equations, but there are many, at least there are 8-9 equations possible. Now, if we closely monitor these equations, we found that for each of the equations, the formation energies are different. So the range of formation energies have an upper bound and a lower bound. And we need to pick the formation, the correct equation, correct chemical path will be that will give you the formation energy close to 0 or higher. Okay, so you should not take a particular chemical path which gives you a very low formation energy. That can be misleading. So we need to figure out the upper bound. So with that, we found that this particular combination Na2O, Y2O3, CO cobalt plus tungsten O3, this particular chemical pathways is giving you a formation energy -9 eV per 5 atom cell. All other chemical equation paths giving you a much lower formation energy, but still then we compare this.
Saurabh, your 20 minutes is over. So please.
20 minutes over?
Yeah.
Is it? No, it's showing only 13 minutes. Oh, okay.
Yeah, your 20 minutes is over. You have 5 minutes including questions.
5 minutes.
Yeah.
Okay.
5 minutes including the questions. Yeah.
Yeah. So give me 5 minutes. Okay, I'll just finish it. Oh, I'm sorry. So okay. So we designed this polar metals and some of the insulators, some of the metals. So now this equations, this part of the work has been done with the collaboration with Tokyo Institute of Technology. And then really what we try to understand is that what is basically causing this cation ordering. So from our structural analysis, what we have found that this particular antiferroelectric distortion is basically responsible for the cation ordering. With that, then what we did collaboration with the Oak Ridge National Laboratory. We collaborated with Dr. Anna Ghosh, and then we try to understand that what is exactly the mechanism which is responsible to understand the cation ordering. So with that, we studied this using machine learning technique, and then I am going to skip that machine learning introduction. So what I'm going to see, this is my overall framework of the machine learning part. So we build a large compositional space, and then we took different features and like structural distortions, other geometry-driven features, and with the machine learning we build a model. We basically try to build a classification-based model because we want to classify different orderings. This is layer ordering, Roxel ordering, and columnar ordering. And this is the data set that we constructed the whole periodic table. What are the possibilities? And we have considered 200 compositions for our machine learning study. And here we have performed actually this work mainly guided by Dr. Anna Ghosh of Oak Ridge National Laboratory. Under her guidance, my student and me were also learning with her. So this is the confusion matrix, and which basically shows you that this diagonal ones basically shows you this positive predictions, and these other non-diagonal terms tell you the false predictions. So we can understand this is the trend set. So we have used random forest classification model to predict to classify the orderings like layer, Roxel, and columnar. And this is my trend set, this is my test set, and we can found that this model is very, very good. So our model is very good, we are happy, but we are not. What we are learning from this model. Then what we came out is basically a quantification of the ordering. So here I can show you that. Just take one example of this particular one, strontium, cerium, manganese, nickel, O6, and here these three values we assigned a probability on it. So this probability for columnar ordering is 9.5, and if you sum the probability of 0, 1, and 2, then it will be 1. So from this probabilistic model, we can see that this strontium, cerium, these manganese-based systems, they don't want to be formed in layer ordering. However, this sodium, lutetium, cobalt W systems, you see the probability of forming is high, so it can form in layer ordering, which also supported by our previous results. So with that, then we did this feature selection, feature ranking using random forest classification model, and we found that these are the three most important structural modes: the tilt, the two-dimensional charge disproportionation, and this antiphonetic cation displacement. There are three important modes which basically decisive modes where when you are trying to classify your system in layer, columnar, and rock-sol. And with that, but are you happy at that point? Because this is basically give you a correlation between different geometry-driven and structural mode-driven features. But the pattern ordering problem is beyond that. So here, this idea came out by Dr. Anna Ghosh, and where we started thinking beyond the correlation of machine learning, and where we introduced what is called a causal model. Causal model means basically the relation between cause and effect. So what is basically causing? So my target property is, say, a columnar ordering. That is my target. And I start with the tilt distortion. Then what is affecting me to get a clear columnar ordering? And that is the tilt distortion can directly lead to a columnar ordering, or it can lead to via a two-dimensional charge disproportionation mode, and then to the target property. So this kind of causal model is basically gives you a very dynamic behavior that how your cause and the effect are related in terms of for a stable ordering. And this kind of analysis is very important. And we need to think beyond the correlation to get the exact dynamic behavior in a cation ordering problem. So with that, so with that, I have to summarize that from the first principle insights from the first principle. What we have considered, what we have found is that mainly that 3D 5D systems are mainly important for get a clear A-side ordering. So the idea is that the rule is that if you want to get a clear A-side ordering, you should first get clear B-side ordering. B-side rock-sol ordering prefers A-side layer ordering. That is that hint we got from the first principle calculations, and we also identified a mode which is basically the O-side displacement, antiphonetic O-side displacement, which is responsible, which is more crucial for stabilizing the A-side ordering. But we go beyond the conventional first principle calculations. We collaborated and we perform the machine learning calculations, and in the machine learning calculations, we make a very large compositional space, large feature space, including different kind of informations like coordination, a lattice parameter, bond angle, tilt angle, then all the other structural modes. And we found that we were able to rank the features, which features are important for a clear classification between layer, rock-sol, and columnar ordering. But not, we didn't stop there. We went beyond, and then we are now trying to understand the causal behavior of this cation ordering, that what is the cause and what is the effect, that we can precisely tune the ordering in AA prime, BB prime, O6 double perovskites. So with that, I want to thank my funding, ACRB, National Supercomputing Facility, NARSC, SRM. Oyana wants to thank this US Department of Energy, DOE Office of Science, and CNMS user proposal. We wrote a proposal in CNMS in Oak Ridge, and she's the co-PI, she's the PI and the co-PI. And this is the publications, recent publications from my group. Thank you for your attention. And I really thank to Mukulda for giving me some extra time. Thank you.
Okay, Saurabh, thank you for a nice talk. And maybe we can have a very short question if there is any. Yeah, please unmute yourself and go ahead and ask. So if there is no question, then let me ask Saurabh a question. So I was wondering, Saurabh, so for how this cation disorder or ordering, okay, or lack of it, okay, how does this affect your final electronic properties?
Yeah. So the so basically so final electronic properties mean what you're talking about this electronic structure or this
the electronic or magnetic structure, whatever.
Yeah. So here, so this is the 3D 5D system. So here we can found this whole 12 compounds that we have considered. So manganese, iron, cobalt, nickel, and W rhenium, osmium. So here we found that this rhenium-based, osmium-based system is metallic, but you have still the polar distortions. They are polar metals. But this manganese and cobalt-based systems, tungsten-based systems, they are insulating. So they are basically polar. They are basically magnetic polar insulators.
No, Saurabh, I'm asking that keeping the chemical entity same.
Yeah.
Okay. If you compare your ordered and disordered material, okay. So how the electronic properties fare there?
Yeah. So when you actually did this disorder effect, when we did this disorder effect, when we basically did this disorder effect, we have considered G-type magnetic configurations, and then this magnetic configuration retains the same. We really didn't look into the electronic structures of these disorder phases. We only computed the energies, keeping by making sure that this magnetic ground state should not change.
Okay.
And then we compare the energies. So, but we really didn't look into the electronic structure of those.
Okay, very good. So I'm assuming that there is no other question. Then let us thank again all the speakers of the session, Nirmal, Sharup, and Saurabh once again. Yeah, and thank you all for attending till late today. Yeah.
Hello.
So,
Sure. Thanks, Mukul, for chairing the session, and for the thanks to the speakers for nice talks. So let's close the session for today. Tomorrow we resume at 9:30. So good night. We'll see you guys tomorrow.
Yeah. Thanks, Anamitra, for organizing very nice conference. Yes.
Sure.
Once again.
Thanks.
Yeah.
Sure. Okay.